Suppose we want to test whether there is statistical difference between two or more population means. So to do this, there is a technique called analysis of variance or ANOVA. So ANOVA is an extremely powerful and widely used procedure, and in ANOVA it works with analyzing the sample variance. So basically we will calculate a lot of, we will use a lot of formulas to set up the ANOVA table. If there is only one factor with two or more treatments, then one-way ANOVA is used in order to determine whether their population means could be equal. And a one-way ANOVA be applied to compare treatments that cannot be randomly assigned. So example, we want to compare the starting salaries among graduates from various fields of study. So our population would be those graduates from example from science, and then graduates from arts, and then graduates from social science. So here we have three treatments, whereby the first treatment is the field of science, second treatment is the field of arts, and third treatment is the field of social science. And we have only one factor, which is the starting salaries among the graduates. Assumptions of one-way ANOVA is that the populations are normally distributed, population variances are equal, and the samples are independent. So this is the framework for one-way ANOVA. Okay, so we have population 1 until population K. Okay, and then example, just now we are using population 1 is graduates from science, graduate from arts, and example, the third population is graduates from social science. So we have all the data on starting salaries, and from the population, when we if we calculate the population parameter, the mean it will be mu1, and the variance will be sigma squared 1, and then so on is the same. So example here for the third population, it will be the population parameter, the mean will be mu3 and also sigma squared 3. But then usually we don't have the population data, we have the sample. So we are taking the sample from population 1, sample from population 2, and sample from population 3. So these are the independent samples. So from the sample, we can calculate the average, the mean, the x bar. So if we subscript 1 means this is the mean or average of the starting salaries from graduates from science fields of science, and it is calculated from the sample and the sample variance. So we can have the average and the sample variance, meaning that we can have the sample statistic for each of the sample. And as we say before, the population we say as treatments. So it is not a requirement that the sample size from population 1, from treatment 1, from treatment 2, or from treatment 3 is the same. The way to write the null hypothesis and alternative hypothesis for one-way ANOVA, two ways of doing it. The first way is by writing H null mu1 equals to mu2 until mu k. The same for here, and for the first and the second is the same. But for the alternative hypothesis, we can say that at least one means differ, or we can say that not all means or mu are the same. So we can write up like this, or we can even state mu1 equals to mu2 not equals to mu3, or mu1 not equals to mu2 or not equals to mu3. To set up the ANOVA table, there are two calculation that you need to do, the main calculation that you need to do is the sum of squares treatment and also sum of squares error. So it is SST and also SSE. So SST is the amount of variation that is attributable to the treatments. So meaning this is referring to the variation between treatment groups. So we are looking variation between graduates from arts, from science, and from social science. Whereas for SSE, the sum of squares errors is referring to the amount of variation due to sampling error, meaning variation within the treatment groups, variation within uh, group from arts, variation within groups from science, and variation within groups of social science. So the key word here is variation between and also variation within. So for ANOVA table, we need to set up these items, the source of variation from treatments, error, and also total. So we see it as the SST, sum of squares error, sorry, sum of squares treatment, sum of squares error, and sum of squares total. So this is sum of squares, and we have this degree of freedom. So degrees of freedom is k minus 1, n minus k, and also n minus 1 for SST. And we have here this column, the mean square of treatments, mean square of error, and also we have this F stats. So we will calculate this SST and SSE. So if we add up, we'll get SS total. So this is treatments, this is total. And if you look at this row, if you add up this plus this, you'll get SS total. So for degrees of freedom, if you add up k minus 1 plus n minus k, so you have this k minus k goes to 0, so you are left with n minus 1. So basically, if you add the first row to the second row, you get the total row. And then to get the MST, the mean square treatments, is just dividing SST over k minus 1. To get MSE is SSE divided by n minus k. And then when we divide MST divided by MSE, we have the F stats. So this F stats is the test statistic. So we are using F test, and we will calculate the test statistic, which is the F stats. And once we have this F stats, we will compare with the critical value, and the critical value will come from the F table. So the F table will have to find the critical value from the F distribution table. We need to have the significance level alpha, and also we need to have 2 degrees of freedom. So this is the first degrees of freedom, which is k minus 1, which is simply this one, and the second degrees of freedom, which is n minus k, which is simply here. So once we have the critical value, we'll compare with the F stat. So if F stats is larger than the critical value, then we reject H null. So if we reject H null, meaning we are saying that at least one of the means are not equal. So to easily understand how to set up the ANOVA table, we will look straight to the example. Okay, so here, if we read this, a major computer manufacturer has received numerous complaints concerning the short life of its disk drive, and most these hard disks need repair within 2 years. Since the cost of repairs often exceeds the cost of the new disk drive, then the manufacturer is concerned. Okay. In his search for a better disk drive, he finds 3 new products, okay, and he decides to test these 3 plus his current disk to determine if differences in lifetimes exists among the product. He takes a random sample of 5 disk drives of each type and links it with a computer, and the number of weeks until the drive breaks down is recorded and is shown below. So from this paragraph, we understand that the factor that he wants to analyze is the number of weeks until the drive breaks down. So he wants to test whether is there any statistical difference between the number of weeks until the drive breaks down for the four uh, products. So I mean you have that 3 new products and you want to compare with the existing. So we have like 4 treatments. Okay. So this is the data on the number of weeks that the drive will break down. Okay, and we have 4 treatments, which is the first product, second product, third product, a new product, and also the current, uh, the one that is currently used, which is type 4. So we have 4 types of it. Okay, so if you look at uh, from type 1, he's taking 5 samples. So here we are using exactly the same number of samples. And the question is, does this data allows us to infer at the 5% significance level that there are differences among the disk drives? So we want to find out whether is there any statistical difference in the means uh, of the number of weeks of breakdowns among the 4 types of disk drive. So we have this H now, mu1 equals to mu2 equals to mu3 equals to mu4, and we can write H1 as at least 2 means differ, or at least one of the means is different, or we can write as mu1 not equals to mu2 not equals to mu3 not equals to mu4. Okay, so that's how you write for the H now and H1. To set up the ANOVA table, first you need to calculate the average for each of the type. So from the data, you need to calculate X bar for type 1, type 2, type 3, and type 4. And then you calculate the sample variance for type 1, type 2, type 3, and type 4. For example, for type 1, you add up 78 plus 92 plus 101 plus 105 plus 98, and then you add up, sum it, and divide it by 5. And then that is X bar 1. And then you calculate the variance simply by, for each of the term, 78 minus the mean, 92 minus the mean, and then you get the difference, and then you square it, and then you sum it, and then you divide it by n minus 1. So it is simply by using the formula for sample variance. So once you have all the average, the X bar, and the sample variance for all the 4 types, we can get the grand mean. So grand mean is simply by adding all the 20 data divided by 20, or you can simply add up all the means and then divide the average divided by 4. Then you get 110.45.